This is the second of videos looking at titanium oxide. The sample is a titanium foil, a metal foil that has a surface covering of oxide. And the surface is modified by a helium ion beam. And the idea of doing this experiment is to investigate why it is that titanium changes so dramatically when we expose the surface of the titanium oxide to ions. If we would use other ions such as argon, the results would have happened more quickly. So understanding why we suddenly see a change in the titanium while we don't really see a change in the oxygen, for example. I mean, there is some evidence there's some change at the beginning, but that could be related to the carbon. And yes, we see that the carbon does change as a function of the sputter time. So the fact that we don't see a change in the oxygen, but we do see a change in the titanium, is grounds for an investigation of what's going on for this type of sample. And the basic tool for understanding what's happening in XPS is to try and quantify data. So we try to calculate the atomic concentration, that's what we would like to think, but what we are actually doing is we are normalizing the signal with respect to the total signal that we're measuring, and therefore taking out certain artifacts that might be introduced by variation in X-ray intensity, for example. So instrumental factors, maybe sample factors that alter the relative intensity. And so for this depth profile, I'm calling it depth profile, but it's still supposed to be at the surface, this profile we can understand the changes by calculating the atomic concentration and presenting it as a plot as a function of the sputter time. And that's what I'm going to do now. To construct a profile from Spectra, I need to put some quantification items on these VAMAS blocks. So either regions or components. In this case we're just going to use regions. That'll just make it simple. So I need to construct, using the quantification parameters dialog window on the regions property page, a region. I'm using a basic Shirley background, and I can adjust, say, the number of data points used to tie the background to the data. This will stabilize the background calculation and reduce the uncertainty in the area calculated by this region. And then, having created it, the relative sensitivity factor has come in, and that's because we've got a titanium 2P heading above this column, and the heading allows the element library to choose the relative sensitivity and also the name for the region in an informed way. This would not be the case if it was a survey measurement. It would not be the case if I'd merged the VAMAS blocks as I showed in the previous video. But because we have this correlation between the titanium 2P and the element library, when I create the region simply by pressing the create button, I end up with an appropriate region for titanium. And then I can propagate. So I made a selection of all the titanium 2P VAMAS blocks and propagated the regions. So now we see that every single one of these spectra have identically defined regions. Now they don't all have to be identically defined. If we had some reason for adjusting the start and end, then we can do that on a selection basis, looking at different selections of the titanium and propagating to the appropriate VAMAS blocks with the appropriate region. But right now this looks fine. So let's do the same for the oxygen. I create, make an adjustment to the limits. I've overlaid all of these oxygen data so I can see at the same time as creating a region, I can see how it would relate to these other oxygen peaks, and then again propagate. There's the carbon, and once again I want to take in, including this bump here, and the original adventitious carbon before the helium had some influence, and including the shapes that are created following the influence of the helium. So this now provides me with another set of intensities. These are all calculated with the appropriate relative sensitivity factors in all cases, because each column has the appropriate element transition fields that match with the element library. So having created regions, I can select the VAMAS blocks from which I wish to create the profile, go to the Report Spec property page, and then using the custom report to create a profile, I can say I would like to profile regions. This populates the name column table within the custom report. This indicates how I'm going to calculate the intensities for each of these entries within the profile. So I've got the carbon 1s name associated with the region C1s, O1s name associated with the region O1s, and similarly the Ti2P associated with the titanium 2P region. So once this table is created, I can then apply the area report based on the selection that I've made in the right hand side. The result is a table, and this is a table that could be exported to Excel, for example, or we can create from this table, provided we have a suitable experimental variable and the intensities all are as we expect, a profile. And there's a button on the bottom toolbar here that says Create Profile. Now I'm going to use a different one. This is Add Profile. And when I press the Add Profile, you just see that the table just changes a little bit in proportions. That's to show you that something has happened. And when I close that table, I now have a Control plus F8 profile that we see here in the bottom left-hand corner of the display of the Spectra. And that's to indicate that this VAMAS file now has a profile associated with it, which I can view using this button here that says Cycle File Index. So this will cycle between the spectroscopic form of this profile and the depth profile or traces that are plotted as a function of the experimental variable. So when I click this button, we now see a profile that has been generated from the spectroscopic data. So each one of these traces, this represents oxygen, this trace here represents titanium, and then we've got carbon. So we never really get rid of carbon, and yet what happens is we get a ratio between the titanium and the oxygen that is giving us an indication that we really do have a steady relationship between the titanium and the oxygen as we go throughout this profile. Now the reason that I use the Add Profile button rather than the Create Profile is that I wanted to correlate the profile with the spectra. This means that when I click the button a second time, what it does is it takes me back to the spectra, and if I click it again, it takes me back to the profile. And since I'm actually interested in this portion here of the profile, I can hold the Shift key down and drag out two vertical lines before pressing the Cycle File Index button. And the result of that is to select the part of the profile in terms of spectra that I was interested in when I looked at it in terms of the traces as a function of time. So now I have an example of the spectra for which I believe I've got a relatively constant relationship between oxygen and titanium, and that's what they look like. So the next question is, can I understand what is happening over the course of this measurement? We do see some changes occurring, and these changes we might be able to identify some characteristic shapes in the spectra that give us a clue as to what is happening in terms of the titanium and perhaps the oxygen. Mostly the titanium. So I've been able to use the profile to pick out spectra that I might find useful in my data treatment. And that's one of the reasons why we would create a profile of spectral intensities and want to switch between the profile and the spectra themselves. To illustrate why you might want to make a selection of this form, I'm just going to do a very quick analysis of these titanium spectra we see here using principal component analysis. And the idea of using principal component analysis is to try and work out the differences between the spectra as we go through a sequence of spectra. Being able to identify spectra that at first sight look very similar in terms of the ratio between oxygen and titanium has meant that I've produced here a set of abstract factors for which the third one, this one here, looks like noise. So there are only two abstract factors that actually make sense in terms of spectroscopy. The first one, this is mostly like the average. The second one is telling you what's different from the average in these data. And then some proportion of these two different abstract factors will be necessary to reproduce the data that we see here. And if we use two, we've mostly removed noise. And that would be one of the reasons why we would do this. So here I have this selection, the abstract factors. All I have to do now is press the predict using two abstract factors on the toolbar, and I produce a set of spectra that have signal enhanced relative to noise. And this then is in a position where I could perform different spectra and try and understand what shapes lie within the data that I've now selected.